Hi, this lesson is about computing the volume of a solid. So there will be two methods that you'll learn in this course. One is called the disk or washer method, and the other one is called the cylindrical shell method. This lesson is going to focus on disks or washers. So let's talk about the disk method. So when you have the area under a curve, and imagine taking that area and rotating it around a horizontal or vertical line, that area becomes a three-dimensional shape, which we'll call a solid. And so we're going to imagine computing our volume by slicing through that solid in a circular manner. So if you can imagine like a circular saw slicing through a solid and getting a piece of that solid, that piece will be a circular shape with some depth to it. So when you're setting up your integral, which is what we'll use to compute volume, you're going to set it up based off of the formula for the area of a circle, because the face of the disk is a circle. And so that formula is pi r squared. And when you're computing the volume of a disk, since that disk has some depth to it, it'll be the area of the face of the disk times the depth of the disk, the depth being delta x. But just like area, when we talked about Riemann sums, we know that with the Riemann sum, as the number of rectangles used to approximate the area approached infinity, you got an exact computation, and those rectangle widths became so skinny that we said, well, that when that happens, our delta x is our dx. So with volume, it will be the same thing. We're going to have infinitely many disks that make up the solid, and the sum of all of those volumes of the individual disks will give us the volume of the solid. So your integral will be based off of the formula pi r squared dx. So basically, you're going to have to figure out what your limits are, the boundaries of the area that you're rotating. That'll be your a and b in your integral. And you have to figure out what your radius is, or your radii, as you move through the solid. So your formula will look something like this. So your radius is actually going to be your function, because it will be the height of the disk, and this will occur when you're rotating around the x-axis. So we'll be, in this lesson, we'll be either rotating around the x-axis, the y-axis, or some other vertical or horizontal line. So we start with rotations around the x-axis. So when your rotations around the x-axis, you will be setting up your volume according to this formula right here. So below I have a picture of what I was just describing. So imagine that you have your function defined from a to b, and this is your curve. The area under this curve is the area between f of x and the x-axis. Imagine taking that area and rotating it. That's what this little circular kind of arrow is saying. Rotate it around the x-axis, creating a three-dimensional shape. And then this disk that you see here in the middle, in the darker blue shade, this is a representation of what a disk would look like. This disk has a radius associated with it, and the radius is the distance from the x-axis to any point on the curve. So when you start from the very beginning till the end, your radius will change depending on what your function value is. So your volume will be exactly what I stated above. It'll be the integral from a to b of pi f of x squared, because f of x is the radius, dx, and dx is your depth. That's the thickness of the disk. All right, so for purposes of drawing and kind of thinking this through, you're going to want to remember what I'm writing, what I wrote right here in this green box. You always want to draw the representative disk perpendicular to the line that the area is rotating around. So when you rotate around the x-axis, your disk should be facing the way it is here in this picture. It has to be perpendicular to the x-axis. If you were rotating around the y-axis, then your disk would go in this direction. But we'll do examples like that later. Another important thing to keep in mind is that the depth of the disk determines whether you are integrating with respect to x or with respect to y. So since this disk has a depth of delta x, which is a dx, then that means my limits have to be in terms of x. So I have to be looking at these values, not the y values up here. And my function has to be a function of x. Okay, and that'll be important as we start rotating around the y-axis or different horizontal or vertical lines. So you're going to want to keep these things in mind. All right, so here's our first example. Find the volume V of the solid obtained by rotating the region under y equals x squared about the x-axis on the closed interval from 0 to 2. So first I drew a picture of the area. So this is the graph of y equals x squared, and the region from 0 to 2 is the one that I shaded in here. All right, so I'll show you how you want to show that 3D image. So if you're rotating around the x-axis, it means that you have to visualize taking that area and flipping it around the x-axis and going all the way back around so that it's a three-dimensional shape. So when I draw that, that means you want to draw something that looks like a mirror image of what was drawn above. So this is the reflection of what was above. And so now this creates a three-dimensional shape. And then imagine slicing through this shape. So what I'm going to draw right now is my representative disk. And remember, because I rotated around the x-axis, I have to draw my disk perpendicular to that. This disk has some depth associated with it, and that depth is with respect to the x-axis. So if I were to measure how deep that disk is, it would be some difference in two x values. So my depth is a delta x, right? So that's what I wrote here, which means that everything should be done in terms of x. So your limits, your function, and your differential. And the radius of this disk is the distance from the x-axis to the original graph, and that value has the value of x squared, which is the function. All right, so when I plug into the formula, remember it's pi r squared. Your r is x squared. So that means I have to square the x squared. And my limits go from 0 to 2. Those are the x values. And so then here you just square x squared, so you get x to the fourth. And then it's a simple integral. So you take the antiderivative, that's pi 1/5 x to the fifth, plug in your upper limit and your lower limit, and you get a volume of 32 over 5 pi. All right, so let's do another one. We want to find the volume of the solid obtained by rotating the region bounded by y equal to 2 minus 1/2 x, that's a line, x equal to 1 and x equal to 2, so those are vertical lines, and we want to rotate about the x-axis. So this is the graph, the area that we want to rotate. Since this is a linear equation, you only need 2 points to plot a linear equation, so you want to choose x equal to 1 and x equal to 2 to come up with your linear equation. So when you plug in 1, your y value is 3/2, which is 1.5. And when you plug in 2, your y value is 1. So that's what you see here. This is 2, 1, and this is 1, 3/2. Okay? So then that area is the area that is rotated. And since we're rotating around the x-axis, you want to try your best to draw a mirror image of what was drawn above. So, okay, you don't have to be like an artist here. Just do your best to make it look like a mirror image. So imagine that this gets rotated, and now I've created this three-dimensional shape. And then imagine slicing through that three-dimensional shape. So here's my representative disk. And again, that disk has a radius associated with it. And the radius goes from the line of rotation, which is the x-axis, to the original graph. So my radius is the function value, which is the line, 2 minus 1/2 x. And again, this disk has some depth associated with it. That's with respect to the x-axis. So everything should be integrated with respect to x. My limits are going to go from 1 to 2. Those are your boundaries, 1 to 2. All right, so our volume is here on the right. I have the volume is equal to the integral from 1 to 2 of pi. And then don't forget your function or your radius has to be squared. So it's 2 minus 1/2 x squared dx. Then you want to do the algebra from the first line to the next. In other words, FOIL it out. So, and I'm also going to factor out the pi because that's just a constant or a coefficient. So I have volume is pi, integral from 1 to 2 of 4 minus 2x plus 1/4 x squared dx. Take the antiderivative of those three terms to get this line right here. Plug in the upper limit, minus, and then plug in the lower limit. So make sure you distribute that negative to these three terms. Do the arithmetic, and you get 19. The volume is 19 over 12 pi. Okay, so here's another problem with a better picture for you to visualize this. So we want to compute the volume created by rotating y equal to the square root of x on the interval from 0 to 4. All right, so the original graph is the one that you see here with this darker blue line. This is the point 0, 0. This is the point 4, 2. When you plug in 4 into your function, it's got a y value of 2. And then the area is the area between the blue curve and the x-axis. This is the x-axis right here. All right, so this is a representation of what a 3D solid would look like once you rotate it around x. And then I've drawn my representative disk here in purple. So the distance from the x-axis to the original curve is your radius, and that curve is defined to be the square root of x. So again, here's our volume. It's the integral from 0 to 4 of pi square root of x squared dx. So when you square it, it's a very simple integral. You just have to integrate x dx, take the antiderivative, plug in the limits, you get a volume of 8 pi. Okay, washers. So what's the difference between a disk and a washer? So there is a difference because a washer is a disk with a hole in it. So here's a picture for you. So with these types of volumes, you usually have an intersection of two curves where when you rotate that area, you end up with a hole in the middle. And if you want to compute the volume of that solid, you have to compute the volume taking into account that you have to subtract out the volume of this hole in the middle. You don't want that to be part of the volume. So that's what a washer is. It's a disk. It also has some depth associated with it, but it's a disk with a hole in it. So just in terms of practical terms, if you had a circle within a circle and you only wanted to know the area of the circle on the outside, well, you'd be computing the area of the big circle, computing the area of the small circle, and subtracting, and that would give you the part that's shaded here in blue. So when you set up your volume, it's going to look something like this. And this again will be with respect to rotating around the x-axis. You would have to determine your boundaries, which would be the a and b. The pi, f of x squared would be the larger disk. This is as long as f of x is greater than or equal to g of x. And then you would have to subtract out the smaller disk or the hole, which would be pi g of x squared. And then integrate that result. So let's look at an example of washers. So we want to find the volume of the solid created by rotating the region bounded by f of x equal to x and g of x equal to x cubed for x greater than or equal to 0 about the x-axis. So here we don't have obvious boundaries like we did in the first few examples. So first we have to figure out their points of intersection. We did this with area as well. And we do that by setting your two equations equal to each other, your two functions. So that's what I'm doing here. Set x equal to x cubed. Set that equation equal to 0. Factor out an x. And then you get 3 solutions, 0 and plus or minus 1. But remember, I gave you a restriction in the original problem that x is greater than or equal to 0. So you can ignore the negative 1. And we're only interested in the points of intersection at 0 and 1. So for graphing purposes, you're going to want to know what the y values are. So my points of intersection are 0, 0, and 1, 1. And you can figure out the y values by plugging into either f of x or g of x, and you get these two y values here. All right, so that gives us some information about what the graph should look like. So let's look at the graph. So the original graph of the line is here in blue. The original graph of the cubic, x cubed, is here in purple. The area that's bounded by those two lines, and remember these are my points of intersection, 1, 1, and 0, 0. The area is this area that I'm shading right here in red. And then imagine taking that and rotating it. So I drew the rotation in orange to show you that this bottom part is not the original graph. That's what happens when you rotate. And that creates a three-dimensional shape. So I guess kind of looks like a flower. So imagine taking that shape and slicing through it, again, perpendicular to the x-axis, which is our line of rotation. And when I do that, you actually end up with a washer. So my big disc is this one in like this darker pink color. And my little disc, the inside part, the hole, is the darker blue one on the inside. Both of those discs have a radius associated with it. So the radius of the large disc goes from the x-axis to the line in blue. And so that line is the line y equal to x. So that's the radius of the big disc. And the smaller disc, the hole, that's the distance from the x-axis to the purple curve, x cubed. So the smaller disc has a radius of x cubed. So when we set up our integral, we're going to be using what I mentioned above, this formula right here. You have to compute the volume of the larger disc and the volume of the smaller disc and subtract them because you want to subtract out the whole. All right, so that's what we did down here. I have the integral from 0 to 1, remember those were our boundaries, of pi x squared, that's this radius, minus pi x cubed squared, that's the smaller radius. And then the rest of it is a little bit of algebra and then your antiderivatives. So square both of those, and I factored out the pi, that's what you see here. Take the antiderivative, that's what you see here. Plug in your upper limit, which is 1, and then when you plug in your lower limit, well, both of those work out to be 0. So I just wrote the 0 here just so that you see I didn't forget about it. Then you just have pi times 1/3 minus 1/7, get a common denominator of 21, and you end up with a volume of 4 over 21 pi. Okay, so let's do another one with washers. And actually the same problem, except we're going to be rotating around a different axis. So rotating around a different axis does not mean that you will get the same volume. You could, but it usually does not work out like that because the volume that's created from one axis rotation to another is actually different. So if you see both pictures at the same time. This is the picture rotating around the y-axis, and this is the picture rotating around the x-axis. It's not going to be the same result. All right, so this is the first time we're rotating around y. All right, so we already found the points of intersection, 0, 0, and 1, 1. We don't have to do that again. But remember, when you're drawing your representative disk, which I'm showing right here, since I'm rotating around the y-axis, you want your disk to be perpendicular to the y-axis. The depth of my disk is with respect to y. So if you can see here, I tried to color in that depth. So this is a delta y, which means everything should be done in terms of y, your limits and your function. All right, but remember, I stated my function in terms of x, so I need to fix that. So I did that here below. If f of x is equal to x, then that means x equals y. So that one's pretty straightforward. But if g of x is equal to x cubed, then if you solve for x, that means x is equal to the cube root of y. So we want to keep that in mind. So now we have to figure out our radii. So I have a big disk, which is the one here in like this darker pink color, and I have a hole, which is indicated here by this green disk. So the bigger disk, which is the one that you should put first in your integral, is defined by the distance from the y-axis to the, from the y-axis to the cubic. And the cubic is now defined to be cube root of y. So this is the radius of the larger disk, cube root of y. And the smaller disk going from the y-axis to the line, that's the disk of the green circle, is defined to be the x equal to y. So that's a radius of y. All right, so now we're ready to go. My volume has to be in terms of my boundaries. So those are my limits, 0, 0, and 1, 1. So it's the same limits as my previous problem, but that's because the x and y values are the same, but these are y values, right? So those are the y coordinates. So we want to subtract the volume of our bigger disk. So that's going to be pi cube root of y squared minus the volume of the smaller disk, which is pi y squared dy. So you want to factor out the pi and square both of these. So cube root of pi squared, remember cube root of y is the same as y to the 1/3. So when you square it, you'll get y to the 2/3 minus y squared. Take the antiderivative, which gives you this line here. Plug in your upper limit, and your lower limit just gives you 0. So you get pi times 3/5 minus 1/3, get a common denominator of 15, and you get 4 over 15 pi. So remember our previous, let me just make this a little smaller. Our previous volume was 4 over 21 pi, and this one is 4 over 15 pi. So rotating around the y-axis creates a larger volume than rotating around the x-axis for this particular problem, because 4/15 is bigger than 4 over 21. Okay, so let's move on. Here's another one where we're rotating around the y-axis. We want to rotate the region bounded by y squared equal to x. That's a sideways facing parabola. And x equal to 2y, which is a line. And we're going to rotate that around the y-axis. So just like the previous example, you have to find the points of intersection, so set them equal to each other. And when you do, you get two solutions, y equals 0 and y equals 2. Plug in 0 and 2 into either one of the original equations, and you get these points of intersection, 0, 0, and 4, 2. Okay. So my picture is here on the left. So I plotted my line. So that's in blue. This is x equals 2y. You can plot these 2 points and connect them, and that's all you need. And then my sideways facing parabola is this one here in green. It has no y term, so my vertex is at the origin, and it goes through the 2 points that we found of intersection. So the part that you are rotating is this piece right here. Kind of looks like a banana, I guess. And that gets rotated around the y-axis. So I showed the rotation here in orange. Okay, so I recreated it here on the right just so that it's a little bit larger. So notice that when you rotate and if you slice through it perpendicular to the y-axis, you again have a washer. The larger disc is the one in pink. The smaller one is here in this darker, either looks like black or navy blue. I think it's dark purple actually. All right, so the depth of the disk is with respect to y, so that means everything should be in terms of y, including your functions, and so now we have to figure out what our radii are. Now, luckily, these are already expressed in terms of y. We have y squared equals x, and we have x equals 2y. So we don't have to do what we did in the last example. So my radius is based on the distance from the center to the original graph, and the original graph goes all the way out to the line. This is the line. So the larger radius is 2y, and the smaller one goes from the center to the curve, and the curve is the parabola. So this is the smaller radius is y squared. All right, so we use that information in order to set up our integral. Remember, we're integrating with respect to y, so we use these 2 values here for our limits from 0 to 2, not the x values. So we have the integral from 0 to 2 of pi 2y squared minus pi y squared squared. Square both of those before you integrate. So I have the integral from 0 to 2 of 4y squared minus y to the 4th. Take the antiderivative, plug in your limits, and you get 64 over 15 pi. All right. So as I mentioned at the beginning, it is possible to rotate areas about a line other than the x or y axis. And remember to draw the representative disk or washer perpendicular to the line that you are rotating about. So that's always important to get an accurate picture to try to visualize how you need to represent this. So here we're going to rotate the region bounded by x equal to y squared. This is again that same sideways facing parabola. And the line x equal to 1 about the line x equal to 1 and compute the volume of the solid. All right, so first the picture. So the original picture is the one that you see here in red. So it's got a vertex. Y squared has a vertex at 0, 0. And it intersects the line x equal to 1 at 1 and negative 1. So if you plug in 1 for x in here, y will equal plus or minus 1. So those are the boundaries of your graph, and I shaded the area in red. So imagine rotating that around the line x equal to 1. So the rotation is shown here in this lighter blue. And then you have to slice through that. My representative disk is in green, and that disk is drawn perpendicular to the line I'm rotating around, which is x equal to 1. So remember, the radius is the distance from the line of rotation to the original curve. So that's what I showed right here. This is the r that we have to figure out. Now this one isn't quite as straightforward. You have to do a little bit of arithmetic to figure that out. So the distance from the y-axis to the line x equal to 1 has 1 unit. That's 1 unit, but that's not my radius. And the distance from the y-axis to any point on the curve has a value of y squared. So the part that I'm interested in is the part that's inside of this solid. So that radius is 1 minus y squared. The differential, or the depth of the disk, is with respect to the y-axis. Right? If you were to compare that depth over to the y-axis, this is a dy. So that means everything has to be expressed in terms of y. So here's my volume. I'm integrating from -1 to 1. These are my y values. Pi, and my radius is 1 minus y squared dy. So you want to square that first. But I also took a little shortcut here because y squared is symmetric. In other words, the top half of the graph is the same as the bottom half. So you can actually change your limit value from 0 to 1 and double it, and you'll get the same result, and saves you a little bit of arithmetic later on. All right, so that's what we're going to do. We're going to integrate from 0 to 1 and double the result. So here, factor out the 2 pi and take the antiderivative of the 3 terms above. So I get 2 pi times y minus 2/3 y cubed plus 1/5 y to the 5th, evaluated from 0 to 1. You really only have to plug in the 1, because when you plug in 0, all those terms will be 0. So you end up with a volume of 16 over 15 pi. All right, so you're ready to try some homework for this section. Good luck.